All right, so we're in, we'll call this section 13.6. Last probability thing that we're going to talk about for our first unit. We're talking about conditional probability. And we'll also talk about tree diagrams. We used tree diagrams a little bit when we talked about counting principle, but we're going to do a little more with them today. So on our opener, we had this bag with marbles in it, and we picked a red one and then a blue one without putting the red one back. We calculated that probability. Those two events, from what we talked about before, those two events are dependent events, because picking the red marble out, not putting it back, changes the probability of the second thing happening. So those were dependent events. And what we decided when we worked through our openers, when to find probability of dependent events, we multiply the two probabilities. And we wrote that in several different ways. We said that one way that we wrote it was the probability of B given A. And we've been working with this idea of the probability of one thing given another thing with our two-way frequency tables. We can use two-way frequency tables to calculate this. So we said this is the probability of B given A. The other way we could write this is the probability of, these are all different ways that we can say this. We could say this is the probability of A after B, or the probability of B then A. We can say this probability lots of different ways. Probability of B given A, probability of A after B, probability of B then A. We call this probability conditional probability. All of these equal conditional probability. And conditional just means that the second probability changes after the first thing happens. So there's a condition on the probability. Something changes it. And on our opener, we decided that to find the probability of a red and then a blue, what we call the probability of A and B. So for our opener, we calculated the probability of red and blue. In two picks, we wanted the probability of red and blue. And the way we solved our opener was we found the probability of the first thing, the probability of A times the probability of B after A. That's how we found our probability. Probability of red and blue was the probability of red times the probability of blue after red. Well, what we're going to do today is rearrange this so we can figure out just this second part. What if we know the probability of both things happening and the probability of one of them, and we want this conditional probability? What I'm going to do is divide both sides by the probability of A. So divide by probability of A, and I'm going to rearrange this. I'm going to write this side first. When I divide both sides by the probability of A, I get the probability of B given A is the probability of A and B divided by the probability of A. When I divide this equation, I'll write it in here in red. Divide by the probability of A. The probability of A on this side cancels out. And then I just rearranged it. So the probability of B given A is the probability of A and B, one thing happening and the other thing happening, divided by the probability of A. This formula is called our conditional probability formula. Yes.
Why do you have to divide by A?
On this side of the equation, it doesn't cancel.
I see.
Right. I just turned it around. Yes. Good question. So this is our conditional probability formula. So if we know the probability of both, and we know the probability of A, we can find this conditional probability. So that would be like on our opener, if we already knew our answer, we knew 5/44 was our answer, and we knew the probability of picking the red marble, we knew that is 5 out of 12, we want to figure out this other probability. So this is how we can figure out that other probability if we didn't know it for some reason.
Can we do like an example of this?
We will do an example. Yes. And a couple more things before the example. This formula, the conditional probability formula, the formulas for permutations and combinations, those will, all three of those formulas will be written on your test. So you don't have to memorize those formulas. So like we did for the quiz with permutations, combinations, I had them on the board. Those will be on your test. This conditional probability formula will be on your test as well. So you have those formulas. So let's look at how we might use this conditional probability formula. For example, we did a test for the effectiveness of medication. So we tested medication. We tested medication on different patients. Half the patients got the medicine. Half got a placebo. Do we know what a placebo is? A sugar pill, or what's another way we could say it? Fake medicine? Or did you have one, Evangeline? To make you believe, yes. It's to make you believe it's medicine, but it doesn't have any medicine in it. So you don't know it's fake. Right. So there's an idea that placebos can have some effect. So the patient thinks it's the medicine, they believe it's the medicine, but it doesn't have any medicine in it. So half actually got the medicine, half got this placebo. The probability that someone got the placebo and got well is 20%.
How do we get that?
From the study, we know that. We saw how many people got well after they got the placebo. So in the study, that's what we found, was that 20% of the people that got the placebo, 20% of the people that got the placebo and got well. We want the probability what is the probability that someone got well given that they got the placebo? So we know that half got medicine, half got the placebo, and we know from the study that out of all the people, out of the whole, everybody that took the study, 20% of them that got the placebo got well. So this is like what we did with our two-way frequency tables. This 20% probability is using the total number of patients from the study. It's like using all the numbers, the total number in the two-way frequency table. The probability that someone got well given that they got the placebo is like looking only in the placebo category. We're looking only at those people, and we want the probability that if we know that they got the placebo, or given that, we're looking in that category, what's the probability that they got well? So this is like we did with the frequency tables, where we're looking only in that category. We're looking only in the placebo category. So our formula our conditional probability formula gives us a way to calculate this. We are looking for the probability of B given A. That's what our question is, the probability of someone got well given that they got a placebo. So I'm going to say that is the probability of got well given the placebo. That's what we're looking for. Yes?
How did you get well?
Sometimes some think that if you think you get medicine, that your body will then actually get well. Maybe you just got well naturally on your own. Maybe the medicine really wasn't that effective and you would get well anyway. So there are lots of reasons why you would get well. And that's kind of that's an interesting question, but kind of separate from a study like this, is why you would get well if you didn't take the medicine. But yeah, that's a good question. So this is what we're looking for, this conditional probability. So we need the probability of got well and took the placebo. All right, the probability of well and placebo. The probability of got well and placebo, what does the problem tell us that number is? What's the probability that they got well and took the placebo? 20%. That's what the problem tells us. So I'm going to say 20%, or as a decimal. What's 20% as a decimal? 0.20. And our conditional probability formula says we need the probability of this second thing. So let me look back at our formula. The probability of B given A is the probability of A and B divided by the probability of A. Probability of the second thing in our conditional probability symbol. So in our problem, the second thing, the given thing, is placebo. So what's the probability that someone got a placebo? Looking at our problem, how many of the patients got the placebo? 50%. Half of them got the placebo. So the probability that anyone got a placebo was 50%, or 0.5. So our formula tells us, our conditional probability formula tells us that probability of well given placebo is the probability of they got well and took the placebo, 0.2, divided by the probability that they got the placebo, divided by 0.5.
How did you get the,
Were you asking about the 0.5?
yeah, then?
Yeah, it says half. So that's how we got that probability. Divide that out, and we get 0.4 or 40%.
So let's see if it was one.
The probability that someone got well, given that they got the placebo, is 40%. So just to re-emphasize what this means, the probability someone got a placebo and got well, that's out of all the people in the study. The probability that someone got well, given that they got the placebo, we're looking at only the people that took the placebo. So that's why they're different. We're looking at only placebo category. Yes, question. The problem, 50%. Up here in the problem, the question was, how do we get 50%? It says half the people got the medicine and half got the placebo. So 50% got the medicine, 50% got the placebo. That's how we got that. Yes, Preston. 0.2 divided by 0.5. Just put that in my calculator and you get 0.4. Yeah, I'm just dividing it. So when we're working with the conditional probability formula, when we're looking for the probability of B given A, we need the probability of both together, the and part, probability of A and B, divided by the probability of the given thing. We're dividing by the probability of the given thing. So if I look back at our formula, we need the probability of both A and B divided by the probability of the given. This is our given, dividing by the probability of the given. All right. Any other questions on the example? We will, I'm going to do a tree diagram and then talk about how the tree diagram is related to what we just did. So something similar, and then we'll do, and relate it back to this.
What's our next unit?
Next unit, we'll actually start talking about geometry. One thing that I want to emphasize about conditional probability, the probability of B given A does not always equal the probability of A given B. They're not the same. So if we switch around our givens, they can be different. An example of that would be the probability that someone owns a car, given that they own a house, is different than the probability that someone owns a house, given that they own a car. Lots of people own cars who don't own houses, but usually people who own houses own cars. So those two probabilities are different when we switch them around. So it's important to remember that when you're thinking about probabilities. All right, let's talk about tree diagrams. Tree diagrams can help us out with conditional probabilities. We use tree diagrams when things can happen in more than one way. So let's look at another conditional probability problem, and this time we'll draw a tree diagram, and then we'll go back and draw a tree diagram for our first problem and show how they help. So for this example, we have a sports team, and they win wins 65% of the games it plays on muddy fields. I'm going to say games in mud. And it wins 30% on dry fields. So for some reason this team likes to play in the mud because they win 65% of their games on the muddy fields. Maybe where they practice is muddy usually, I don't know. The probability of the next game in the mud is 70%. We want the probability that the team wins its next game. So we know it wins 65% of the games that it plays in the mud. It wins 30% that it plays on dry fields. The probability of the next game being in mud is 70%. We want the probability of winning the next game. So we're going to make a tree diagram for this. So here is our diagram. So we know that they're going to play a game. It can either be in mud or on a dry field. What does the problem tell us the probability of the next game being in the mud is? 70%. So what I do is I draw a branch there, and I'm going to label that 70% or as a decimal 0.7. We're only talking about two ways that it can play a game. The team can play a game on a muddy field or a dry field. There aren't any other kinds of fields. So what is the probability that the team plays on a dry field? 30%. They have to add up to 100%. So our branches for our possibilities always have to add up to 100%. That's the only two ways that they can play. Now when they play on mud, they can either win or lose. What's the probability of winning when they play in mud? 65. So I'm going to label this branch 0.65. So what's going to be the probability that they lose on a muddy field? 35. They either win or lose, right? So it has to be 100%. So that's going to be 35% or 0.35. And on the dry field, they win or they lose. The probability that they win on a dry field? 30%. I'm going to label that branch 0.3. So what's the probability they lose on a dry field? 70%, or 0.7. All our branches for our possibilities add up to 100%. All right, so we want the probability of winning the next game. Well, they can win in two ways, right? They can win if they play on the mud, or they can win if they play on the dry field. So we have two probabilities. So let's calculate each probability. To find a probability, we multiply along a branch. So the probability of winning in mud we just multiply along that branch is 0.7 times 0.65. And if I multiply that out, I get 0.445. But they can also win if they play on the dry field. The probability of win plus dry. I just multiply along that branch. 0.3 times 0.3 is 0.09. Now, let's think about these events. Can they win on a muddy field and on a dry field at the same time? No. So what did we call events that cannot happen at the same time? Mutually exclusive. So mutually exclusive is an or probability. They can win on a muddy field or they can win on a dry field. So we're looking at the probability of muddy field or dry field. So when we have an or probability, what do we do with the two different probabilities? When we have an or. Add. When we have an or probability, we add. These are mutually exclusive, so we add. This is an or. We have mud or dry, so we add. So the probability of a win is 0.445 plus 0.09. I add those together and I get 0.535, which is about, if I round it, 54%. So our team has about a 54% chance of winning the next game. A little bit over half, so pretty good. So that's how we use a tree diagram. The possibilities, the different possibilities add up to 100%. To find a possibility along a branch, we multiply. To find the combined probability, we add the two probabilities from the different branches together. We added the probability of a win from this branch to the probability of a win from that branch. No questions on the tree diagram? All right, let's take a look. The last thing I want to do is take a look at how this tree diagram relates back to our first example. So our first example, so we had some person and they either took medicine or they took a placebo. And when they took the medicine, they either got well or stayed sick. And when they took the placebo, they got well or stayed sick. So the problem told us, what was the probability that someone got medicine on the first problem? 50%. So we said half got the medicine, half got the placebo. The problem didn't tell us anything about the people that took the medicine. It only told us about the people who took the placebo. It told us that the people who took the placebo and got well was 20%. So what that means is that whole branch was, the probability of that whole branch was 0.2. That's what the problem told us. The probability of they took the placebo and got well was 0.2. And we needed to find the probability of this branch was 0.4. So we found this one was 0.4. Well, if we look at this branch, 0.5 times 0.4 is 0.2. 0.5 times 0.4 equals 0.2. So if I multiply along that branch, and what we did to find that branch was we did we knew 0.2 divided by 0.4, or actually what we did, 0.2 divided by 0.5 equals 0.4. So the whole branch together on a tree diagram, if we multiply along that branch, that's the and probability. So on a tree diagram, if we multiply along the branch, that's the and probability. The probability of a placebo and got well is the probability of that whole branch multiplying along. The probability of a little sub-branch is a given probability. Probability of someone who got well, given that they took a placebo, was 0.4. So that's the given branch. So that's how the tree diagram relates to our first example. Any questions on that part? So let me look back really quick and review what we talked about with our formula. If we want the probability of B given A, we need to find the probability of A and B. So the probability of the two happening, A and B, and we divide by the probability of the given thing. We're dividing by the and probability, P and A, or we take the and probability and divide by the given probability. P and A divided by probability of A. And this tells us to be given. All right.